Hi, I'm Joyce Jiyoung Whang from the University of Texas at Austin. I'll talk about non-exhaustive overlapping clustering via low-rank semi-definite programming. This is a joint work with Yangyang from Purdue University, Professor David Gleich from Purdue University, and my supervisor, Professor Inderjit Dhillon from the University of Texas at Austin. Yangyang is here, and David is there, and Yangyang also presents some of the slides. This is the outline of my talk. I first introduced the concept of non-exhaustive overlapping clustering and then described the semi-definite programming or SDP for the non-exhaustive overlapping clustering objective function. And Yangyang briefly talked about the low-rank factorization of the SDP solution, and I also explained the experimental results and the conclude the talk. Clustering is a very fundamental data mining task, and the goal of clustering is to find a set of cohesive data points. Traditional clustering algorithms like k-means find a clustering that is disjoint and exhaustive. That is, every single data point is assigned to exactly one cluster. However, in many real-world datasets, the clusters can overlap with each other, and there are often outliers that do not belong to any cluster. So we recently studied the non-exhaustive overlapping clustering, where a data point is allowed to be outside of any cluster, and clusters are allowed to overlap with each other. So for example, in this picture, if we have this kind of input, the result of non-exhaustive overlapping clustering will look like this. So there is one outlier here, and the two clusters are overlapped with each other. To tackle this problem, we recently proposed a simple and intuitive objective function, which we call neo-k-means. The formulation can be viewed as a reformulation of the traditional k-means, where we introduce the assignment matrix U, which is n by k, where n is the number of data points and k is the number of clusters. Using this U matrix and using some simple linear algebra, we can introduce two important constraints to the objective function, which control the amount of overlap and non-exhaustiveness. On the other hand, for the graph clustering objective function, the normalized code is one of the most standard graph clustering objective functions. And we also showed that we can extend the concept of normalized code for the overlapping community detection tasks. And perhaps surprisingly, the weighted and kernelized version of the neo-k-means objective function is mathematically equivalent to the extended normalized code. So this implies that we can apply the neo-k-means idea to both data clustering and graph clustering tasks. And this was published in the SDM SIAM Data Mining Conference in this year. To optimize the neo-k-means objective function, we proposed a simple iterative algorithm we call the iterative neo-k-means algorithm. And in this algorithm, we assign the data points to their closest clusters and update the clusters. And we also satisfy the two hard constraints to meet the amount of overlap and non-exhaustiveness. This iterative algorithm is fast and scalable, but like the traditional k-means algorithm, it can be susceptible to initialization. And given poor initialization, the algorithm can be trapped in poor local optima. So for example, when we studied synthetic data sets like this, where we have 3 ground truth clusters and 4 outliers, when we initialize the iterative neo-k-means with k-means, we observe that it sometimes succeeds in recovering the ground truth clusters, but sometimes it fails to find the ground truth clusters. So here our motivation is that we want to get reliable solutions by using the semi-definite programming technique. So indeed, in using our new methods, we observed that we are able to consistently produce the reasonable clustering results like this. So here our goal is to get more accurate and more reliable solutions by paying additional computational cost. To do that, we first formulate the convex SDP relaxation of the Neo-K-means objective function, which can be globally optimized. But when we solve this problem using some standard servers like CVX, it is very slow and is not scalable. So to scale this problem, we also studied the low-rank factorization of the SDP solution, which can be locally optimized by the augmented Lagrangian method. So let me give you some background about the semi-definite programs. The semi-definite programs are one of the most general classes of tractable convex optimization problems. The canonical form of the SDP is looks like this, where we have linear objective function, linear constants, and the solution matrix should be positive semi-definite and should be symmetric. But as I said, when we solve this problem using the standard servers, it's very slow, so we can just handle the problems with fewer than 100 data points. So to solve larger problems, we can think of the low-rank factorization of the solution matrix. So now in the low-rank SDP, we replace the X with YY transpose, where Y is the low-rank matrix. So now this problem is non-convex, so we can just locally optimize the problem, but we can now handle the problems with tens of thousands data points. So let me describe how we can formulate the SDP for the Neo-K-means. So we introduced 3 key variables to model the assignment matrix U. So the first one is the co-occurrence matrix Z, which is defined by the weight of each vertex, each data points, and the column of each column of the assignment matrix U. So for example, when we have this kind of assignment matrix, when we consider the first cluster, X1 and X2 occur together. So the first part of the Z matrix looks like this, where we have non-zero structure in this area. In the second cluster, X2 and X3 occur together. So now we have non-zero structure in this area. And we sum these two matrices to get the Z matrix. And we also need 2 vector variables, F and G, where F controls the amount of overlap and G controls the non-exhaustiveness. So for example, in each entry of F vector indicates the number of the number of clusters a data point belongs to. So here X2 belongs to 2 clusters, so we have 2 here. G controls the non-exhaustiveness. So if, for example, if here X4 doesn't belong to any cluster, so we have 0 for that data point. Using these key variables, we can first formulate the SDP-like formulation for the Neo-K-means objective function. So the first 3 constraints indicates that the Z matrix should arise from the assignment matrix, and the constraints in the green box indicates the overlap and non-exhaustiveness constraints. Finally, we also have these 2 hard constraints, where the rank of Z matrix should be equal to K, and the vector G should be in this form. So since we have the rank constraints and integer constraints, this is non-convex, and this is the combinatorial problem. So to get the convex relaxation of the Neo-K-means, we need to relax the last 2 constraints. So now we drop the rank constraints and relax the constraints on the G vector. And now we reach the convexity. So, but as I said, it's not scalable because the number of variables in this problem is quadratic in the number of data points. So now we need to think about the low-rank factorization of the SDP solution, which Yangyang will present.
Thanks. So the low-rank SDP is a standard technique to tackle large-scale SDP. So here we propose optimizing a low-rank factorization of the solution matrix Z by YY transpose, where Y is an n by k non-negative matrix. So now the problem is in a standard form of the minimization problem. with explicit select variables to convert the inequality constraints to equality constraints, as well as the simple bound constraints. So even though now we lose convexity by formulating the low-rank SDP, this nonlinear programming problem only requires linear memory. So, and the existing nonlinear programming techniques allow us to scale to the large problems. So next, to solve the Neo-Hemmings low-rank SDP, we use the augmented Lagrangian method. It minimizes a sequence of the augmented Lagrangian subproblems like this, and that includes the current estimate of the Lagrangian multipliers, as well as a penalty term that derives the solution towards the feasible set. To solve these subproblems, we use the limited memory BFGS with simple bound constraint algorithm to solve this. And it requires the computation of the gradient for the variables of this augmented Lagrangian functions. So as we will see that it's not trivial to add the gradient, so we determined and validate a negative form of the gradient for the variables. And so the other details of the augmented Lagrangian method to solve the low-rank SDP for Neo-Hemmings can be found in our paper. And next, we want to see the validations of our LSDP server. So here we consider two small graph clustering problems, which can be handled by the CVS. So, and we also consider the different configurations of with He, alpha, and beta. So here we compare the runtime of these two methods, and we can see that our LSDP is roughly an order of the magnitude faster than CVS. And we can also see that the objective values obtained by our LSDP server and also by the CVS server are quite similar. So that means in these cases, our LSDP server can get the solutions that are as good as the global optimal solutions obtained by the convex servers. So after we add the LSDP solutions, we need a further step to run the solution to binary cluster assignments. Then we can use this LSDP solution as the initial cluster assignment for the interactive Neo-Hemmings procedure to improve the solution. In the practice, for the data clustering problem, we can also run the LSDP on 10% of sample of the data points, then use it as the initialization for the interactive Neo-Hemmings algorithm. And for the graph clustering, we can also use the two-level hierarchical clustering for the large problems. So next, Joyce will continue to present the experimental results on both data clustering and graph clustering.
Okay, now let me show you some experimental results. So first, we studied the synthetic problems on overlapping community detection task. Here, we create ground truth overlapping communities and measure the errors as we increase the noise levels. The red line indicates the simple iterative Neo-Hemmings algorithm, and the blue line indicates the LSDP method. So we observed that we can reduce the errors in finding the ground truth overlapping communities by using the LSDP method. We also studied the real-world datasets for data clustering task. We first compared the Neo-Hemmings objective function values. So here we compare the three different methods. It's just three different initializations. So for the baseline is the K-means initialization, and we compare it with the LSDP initialization and also LSDP initialization with sampling technique. And we observed that we could get a better Neo-Hemmings objective function values using our LSDP methods. In these data sets, there are ground truth clusters. So we were able to compute the F1 scores. And also we compare with other state-of-the-art clustering, overlapping clustering methods. So the first observation was that the neo-K-means-based methods outperform the other clustering methods. And also we observed that using the new LRSDP approaches, we could improve the F1 scores. Finally, we studied the graph clustering problems on real-world social networks. Here we measured the conductance versus graph coverage metric. So the conductance is one of the standard ways to evaluate the quality of overlapping the quality of communities. And here we first sort the communities according to the conductance and greedily take the communities until we cover a certain percentage of graph. So the resulting graph look like this. And the lower curve indicates better communities. So we compute the area under curve score for each plot. And we observed that on 4 different real-world social networks, the LRSDP method could achieve the lowest AUC score, which means that it produces the best quality communities in terms of the conductance. So let me conclude the talk. In this paper, we proposed the convex SDP relaxation of K-means like algorithm that handles the overlap and non-exhaustiveness in a unified framework. And we also studied the low-length factorization of the SDP solution to scale up the problem. And we also studied a series of initialization methods and rounding procedures that enable us to accelerate the convergence of our optimization procedures. And the experimental results show that our approaches give more reliable solutions on both data clustering and overlapping community detection problems. And this is my homepage, so I'll upload the slides and the codes will be available soon. Thank you.
So thank you. There is time for questions. It was not so easy to follow. I mean, I would like to know whether how much do you really rely on enhancing K-means with this clustering? I mean, if I looked into what you presented afterwards, I thought you don't need to take K-means as the basis.
I'm sorry. The K-means? So could you repeat?
You had at the beginning talking about K-means and that you want to move faster because you don't want to have it separate. But then in the end, you did not compare the final task to what would be done if you would have taken K-means.
In the overlapping community detection part? So here, the K-means only generates the disjoint and exhaustive clustering. But here, we want to find the overlapping communities. So
yeah, my question is, in a way, what do we get? So the background is that I also work on overlapping clustering. And it is hard to prove why you want to have clusters overlap. So that was why I'm asking, in which way does it help that you allow for overlaps?
Oh, okay,
and
good.
Did you compare to what would happen if you were not allowing overlaps? So that's the long version of my question.
Okay. So there are many practical applications where the clusters are overlapped. I mean, so for example, in the biology, so each cluster can correspond to each functional class. And like when we consider the gene network, for example, one gene can belong to multiple clusters, not just one functional class. So that is one practical application, and there are many other applications also. So I'll be happy to discuss that offline. Yeah.
But in this Facebook, would you lose any accuracy or any evaluation if you would say, well, we make it just separate?
So I mean, the goal is to find the overlapping communities because, like in the community detection task, each community corresponds like social circles. So we naturally belong to multiple communities, not just one community. So yeah, that's the motivation of the work.
So you say it is just the task is really requiring that there are overlaps, and that's why.
Yeah, there are many examples.
Yes.
Right.
Yes.
Thank you.
So another question? Maybe more technical? No? Okay. So let's thank the speaker again.